I'm going to actually leave the opener for you guys today. Go ahead and complete it. Determine if the following polynomials are function or are polynomials or not, pardon me. If so, identify the degree, the lead coefficient, and the constant. If not, explain why. All right, so today we're shifting our attention from polynomials to power functions. And power functions, we merely need to adjust our thinking from does it have a whole number exponent or does it just have an exponent, and specifically a number in the exponent. So 2 over x to the fourth can be rewritten as 2x to the negative fourth, just using properties of exponents. So this is a power function. So things we were excluding before for polynomials are now being included in the power function family. So identify the power. The power is negative 4. The constant of variation, I'll say COV, is the 2. And then the independent variable, well, that's less exciting. That's just x. So we'll say that is our ironclad answer for all of those, and we won't touch on it again. All right, 5 square root of x. This can be written as 5 times x to the 1/2. So this is also a power function. Our power being 1/2, and our constant of variation is 5. Constant of variation, think similarly to lead coefficient. All right, so then we got 3x to the 7th. So is a polynomial a power function? The answer is sometimes. In this case, it is. So our power is 7, and our constant of variation is 7. No, just kidding. It's 3. All right, so let's look at the last one. Is this a power function? And the answer is no, it is not. Why isn't it? So what's different from this one? It's got the exponent. It's got a lead coefficient or constant of variation. The difference is we have this minus 3 here. We have 2 terms. Power functions, we have 2 terms. I'm going to let that go. It's now on the internet for the rest of the time. We have 2 terms. I'm going to even misspell 2 while I'm at it. There we go. We have 2 terms. And when we're talking about power functions, we're talking about strictly 1 term. So determine if the following are power functions or not. Okay, so the first one is no. The variable is in the exponent. We always want a number in the exponent. Is in the exponent. What about this next one? The answer is yes. Our power being negative 2/3, and our constant of variation is 3. What about the next one? We got to think in terms of numbers here, and the answer is yes. Our power is pi, and our constant of variation is the Euler number E. This one you can see on my classroom, 2.718, blah, 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 blah. And then finally, the last one is no. Again, we have 2 terms. There we go. So determine if the following are monomial functions. Now, with monomials, we have to adjust our mindset back to polynomials. So monomials are single-termed polynomial functions. So the answer here is no. We have a variable in the denominator. This one, yes, monomial. Again, we're adjusting our mindset back to polynomials and looking for a single term. So that means this one here, 5 square root of x, is yes, just kidding. It's no, we have a radical. And then our final one is, you guessed it, also no, because monomial, again, are single termed. We have 2 terms. Pardon me, I misspelled that. We have 2 terms. All right, so monomial functions, give these a shot. So 3 times 2 to the x, no. The variable is in the exponent. This one down here, yes, it is a monomial. Again, e and pi look weird in a polynomial function. Oh, wait, sorry, no, not a polynomial function. I was still stuck in my mindset of power function. So no, this is not. The exponent is not a whole number. The exponent is not a whole number. And then we can draw that same explanation up here. No, the exponent is not. And then finally, we just had a group of no's. No, we have 2 terms. All right, so let's complete the table below and let's kind of draw some connections on the next 2 problems. Let's start with domain. Now, the first 2 are polynomials. X squared and x cubed are polynomials. The domain of all polynomial functions is all real numbers. This was something we talked about in the previous unit. Now, the ranges are different. For every odd degree polynomial, the range is also all real numbers. That's easy enough to remember. For even degrees, though, for the monomial specifically, we're going to look at the range being from 0 to infinity. We can kind of draw ourselves a little graph and remember that that is a horrible graph, but you know, I can do better. I didn't mean to reset the whole screen. I just meant to erase that graph. I thought that was an undo button. But there we go. So negative infinity to infinity. We start at 0 and go all the way to infinity. This was negative infinity to infinity. And this was negative infinity to infinity. Now, odd, even, neither. Well, this must be even because the exponent is even, right? And that is true. Whenever you're talking about monomial functions, you can tell if it's odd or even based on the exponent, which means this right here is even. Just kidding, it's odd. All right, we're on a roll. Let's look at 1/2 power. Now, you can check these graphs on Desmos. It's too complicated for me to be switching back and forth, so I'm just going to draw them from memory. We get that. Now, that is not all real numbers. That starts at 0 and goes to infinity, and so does the range. It goes from 0 to infinity. And looking at the symmetry of the graph, there is no symmetry, so when I say look at the symmetry, I mean lack thereof. Now, 1/3, that would look something like this. And while these are pointing left and right, they're also pointing up and down. So once again, we have a range and a domain of all real numbers. And then odd, even, or neither? Well, it's kind of, I mean, not based on my drawing. Don't base it off my drawing, but we have this odd symmetry. If I flip this upside down, it would be the same graph. So x to the 2/3. Let's see if I can draw x to the 2/3 from memory. That kind of looks like a strange curvy looking V. And we can see goes left to right in infinitely many directions. So we still have negative infinity to infinity for its domain. But we no longer have all real numbers. We're starting at 0 again and going to infinity. Now, it does have the y-axis as a line of symmetry, so that would make it even. Now, what about some power functions with negative exponents? Well, let's go ahead and look at this is x to the negative 1. We have to remember exponentially, that's the same as 1 over x. Okay? And this is not all real numbers. We start at negative infinity. We can see we have that vertical asymptote there. So right squishily, but we got negative infinity to 0 and then 0 to infinity. Now the range is the same thing because we've got the horizontal asymptote there messing things up. And then this is an odd function. Now, in a power function where the exponent is odd or even, you can base it off of the same way we did with polynomial, or monomial, I should say. And then I always thought this graph looked like a volcano. We got the same domain. Can I get it in there? Kinda. When I told you all polynomials have domains of negative infinity to infinity, all power functions with negative exponents, negative whole integer exponents, will have the same exact domain. So you can kind of make that a fact and stamp it in place, although our range ends up being from 0 to infinity, and we have that line of symmetry at the y-axis, so this is even. So go ahead and try to complete this table next. I encourage you to try and draw conclusions from this table to this table and see if you can see similarities in graphs and therefore similarities in the structure, and can we get similar looking answers? All right. Domain. Two polynomial functions here. If you said negative infinity to infinity, you are right. Now the even degree, I'll even write it down, even monomial will always have the same range of 0 to infinity. You can put that as a fact. And then the odd degree monomials will always have all real numbers as their range. So those are kind of stamped in place. We can set those in stone. Okay. Now 1/9, that ends up being negative infinity to infinity and negative infinity to infinity, and it is odd. Notice this is a similar answer to when we had, there it is, 1 over 3. When you have, now remember when we're talking about rational exponents, we're talking about simplified fractions. When you have odd over odd, you're going to have those properties. Okay, set that in stone. Let's go back over here to these odd and even negative integers. We know, I told you the domain of those would be the same. And let's see if I can fit it in here. No. Yes. All right. With an even exponent, we go from 0 to infinity, and from an even negative integer, 0 to infinity, and an odd negative integer, our domain is the same as range. And this is even, and this is odd. Now, we had something like this before. On the previous one, we had an even exponent divided by, or an even numerator and an odd denominator. And this was the result, and that's because we're taking negative values and squaring it. So we can carry these properties over at the same time. We can still plug anything we want into this. So let's go back. So we get negative infinity to infinity. We've got 0 to infinity. We're only going to get positives out because if we're plugging in negatives, we're getting positives out because that 2 that's squaring everything. And then this is also even. And then finally, an odd over an even, we can kind of copy that based off of this right here. Okay, so we have 0 to infinity, 0 to infinity. I feel like I'm forgetting a combination, and this is neither. So for the exit ticket for the given power function, determine the constant of variation, the power, the independent variable, its domain, range, and if it's odd, even, or neither.